All right. All right. Welcome to our first undergrad colloquium. And so let's see, today our speaker going to be Professor Anuj Mumbai. Am I pronouncing your name correctly?
Perfect.
All right. And Dr. Ackman going to introduce Dr. Anuj Mumbai. All right. OJ. Bob John, you mute yourself. And can you tell him to?
Okay.
All right.
Yep. Thank you, Gail, for seeing to it that Anuj actually shares his wisdom with us. It's my honor to introduce Dr. Anuj Mumbai. He is not just a biomathematician. He is close to our hearts. But before I go over our personal connection, I'll very briefly go over his credentials. We don't have enough time to go over all of his credentials. He has a very esteemed place in the world of mathematical biology. He is currently an associate director at Precision here of Precision Medicine Group. And we are lucky to have him as an instructional assistant professor in our department and a visiting scholar of the Center for Collaborative Studies in Mathematical Biology. He joined us from Arizona State University, where he was co-director of the Simon Levin Mathematical Computational Modeling Science Center and the School of Human Evolution and Social Change. He was part of this assignment. He was also co-director of or director for a while, and then co-director of Mathematical Theoretical Biology Institute, MTBI. He served in MTBI for 6 years from 2014 to 2020. So one of the activities of MTBI is holding REU research activities, annually research activities, two of which my son Devin attended and had Anuj as his research mentor. And so I think Anuj was the one who sparked the research flames in Devin. And after he was done with Devin and pushed him to a PhD program in ISU, he got to me and we started working together. I actually got the honor of being part of the MTBI program during the last 2 years. And his energy, his activities on all of these mathematical biology is unmatched. As under his leadership now, IBA, our Intercollegiate Biomath Alliance, and a couple of universities, for instance, University of Wisconsin, Whitewater, George Mason, and Arizona State, is currently holding a webinar series on various aspects of COVID-19. The series is called Battling Emerging and Re-emerging Epidemics and Designing Mitigating Strategies. So with that, I am really honored to welcome him and will be looking forward to his talk.
Well, thank you, Professor Ekman. This is very honored, and it's for the kind introduction that you have given. And this is my first actually interaction, at least some form of face-to-face with others in the department. So my heartiest greetings to everyone. And thank you for inviting me to give the talk in this undergraduate colloquium. Gail, especially to you, communicating with you on various aspects of this colloquium, and thank you very much. And before that, Professor Sillinger, I've been communicating with him for joining the department, and it's my pleasure and honor to be a part of this incredible department. So thank you for having me for that same. And well, I was thinking about what would be the best thing to introduce myself to everyone and to my research that I do. So Professor Ruckman, I'm working on many ends with Professor Ruckman, but today I kind of shortlisted very briefly so that students could also get to know me, what aspects I've been working on and how do I work on things like related to mathematical models of very, very complex systems, from infectious disease to social science to even some engineering problems. So I've been part of, so before that, I will have some description about my background in a few minutes. So, well, almost all the mathematical modelers are working in COVID nowadays, almost all. But the flavors are different from one person to another person. And I think what I see is mathematical modeling for the diseases is from understanding what is the ground realities in the COVID times. That is very, very important, which sometimes we think about equation as the main focus rather than ground realities. So that is very, very important. And then also storytelling about what implications can be drawn from whatever the mathematical results are telling you. And that is a huge lot of deal. And by publishing papers in an applied journals or journals which are non-mathematicals is very, very challenging, especially from a background in mathematics. So with that, let me, so I'm attached to also to, as Professor Ruckman was saying, to Precision here, where I'm, it's an industry of working in health economics. And I do lots of health economics problems, especially related to COVID-19 on that. And but also I'm part of College of Health Solution at Arizona State University and Prevention Research Center, Berkeley, which is a National Institute of Alcohol Abuse and Alcoholism Institute, NIH Institute in Berkeley. So let's see my next slide. Talk too much. I've been part of 2 NSF grants that was just funded recently. One is called Expedition in Computing. It's at University of Virginia. And there are lots of institutions that are part of this. And the whole idea, it's a $20 million grant. So it's a huge, massive grant where many, many institutions have been involved in. And I have been also part of some aspects in that grant. And grant that is a COVID rapid grant, which I was a PI, but and it is actually studying air travel and how is the viral propagate in air travel, during air travel, actually, what aspects guides the travel, what can you do to prevent it, and so on and so forth. It's called VIPRA. This NSF COVID rapid proposal is called VIPRA, VIPRA, viral infection propagation through air travel. And the third, of course, last but not the least, most important one is Intercollegiate Biomathematics Alliance, which Professor Ruckman is leading. I've have an incredible experience with working in this, either through being part of the editorial board of Letters in Biomathematics or being participating in a beer conference, which is also organized by the organization. So thank you for having me for that. So, okay. As Professor Ekman was mentioning a few minutes ago, I was running this MTBI REU program, Research Experience for Undergraduate. It was NSF and National Security Agency and one more funded program. It has a long history, initiated by Professor Carlos Castillo Chavez, but later part I was running it at Arizona State University. The whole idea was very different than what we do it in a regular classroom, and it was involving research very early on, very practical research, data oriented, working with empirical scientists. And not only that, I mean, we graduate with our PhD program or graduate programs from our institutions, but we do not, I mean, especially me, I never got a formal mentoring training while in the graduate program. So we provide a very thorough mentoring program for our graduate students through this programs by them leading the groups or training them in a various measures that would be helpful to them in a later on when they will become a faculty. So there's many levels of mentoring involved in it, from high school students, even some of the high school students are involved sometimes, to undergraduate students, to graduate students, to early career researchers like postdoctoral fellows, to faculty. And sometimes we have social science workers giving a talk on how they collected empirically the data. We have epidemiologists coming into field. I mean, it is very interdisciplinary, truly interdisciplinary, and it builds us, and support staff is there. And sometimes students have very difficulty in approaching us directly, but they can approach graduate students early on. Like instead of undergraduate approach, faculty approach graduate student, for example. So these are a few of the aspects. I've worked with the students on many levels, many different types of projects, like HIV, leishmaniasis, and my main primary area has been working in not only infectious disease, but there is a subcategory called as neglected tropical infectious disease. So leishmaniasis and Chagas disease are the two neglected tropical diseases, and which I've worked primarily. But also social science like alcohol drink association with prevention research and plays through projects like this, and we have National Institute of Alcohol Use and Alcoholism Research. So, how do these college drinking propagate? What from mathematical angle, what in understanding problems, which has been linked on from a long time. We have studied high school drought rates and social medias. How is the information propagate in the social media? So this talk, and let me keep a tab of time as well. So, so today's talk, I will talk about groundwork, and it might be very basic for you, so pardon me in advance. But I wanted to be reachable to everyone. So talk about history of pandemics, mathematical model, evolution of models in infectious disease, and what is the aspects that as a mathematician think about, and not as a, I mean, some we think that we can do some of those things which is meant for empirical scientists or a mathematical model. Certain questions are meant only for empirical, and certain questions are meant for a mathematical. And then what goes in the nuts and bolts in the mathematical models, and I'll talk about examples from my research fields. So, well, this is nothing new. This is nothing new that these pandemics, although it has been many of those one in the past. I mean, if you see on the, let me see if, can you all see my cursor? Yeah, okay. So on this side is a death toll, and this time is a timeline. So like, for example, Spanish flu was in 1918-99, which is this, and death toll was 40 to 50 million. So the size of this virus is very large. So the death toll defines this picture. In this picture, how large was this? So there was 40 to 50 million people died in that. And so the size is very large. HIV/AIDS also, many people died, and these are viral diseases, by the way. And these are how various outbreaks have evolved over a period of time. In fact, in the last 2 decades, starting from 2000, there has been many outbreaks, like Ebola outbreak, MERS outbreak. In fact, as a mathematical modelers, we have been knowing these things for a long time. And we knew, for example, like something like COVID will strike us. But I think the issue becomes how we were prepared about it and what we were doing. And I will talk about it preparation-wise in a few seconds. So just wanted to say that we should not be surprised by this picture. In fact, on the other hand, mathematical models have evolved in a multiple dimension. So if you see in this picture, it has evolved, different methods have evolved from combinatorics to graph theorics to game theory, operation research, dynamical systems, statistical mechanics, differential equation. Now, why are we talking about this? Because real life is so complex that we cannot be stick to one particular field. If you want to address truly a research question, there has to be a cross discipline, not only between mathematics and other discipline, but within the mathematics, different fields such as this. So, so my research follows stochastic process and differential equation. That has been the primary. But with my experience in different application of the diseases, I have able to use many methods in other areas such as graph theory or operation research, for examples. In fact, current methods are focusing on about using some kind of complex systems perspective, which involves networks. And that is the latest way of looking at those ones. Well, in 1960, the latest in the last 50 years that if we talk about how things have evolved, how things finally, what type of models that we are talking about. We are not talking about differential equation type model. We are talking about complex system dynamics models, which involves partly hybrid. It's a hybrid of many fields. It could take probability, game theory, and dynamical system, for examples. And so you need understanding of those systems in some areas, and that's why many of the students in the departments are taking different types of courses. So why do you need to take these courses in different disciplines? That shows you cannot model today's challenging problem unless you are taking some of the basic course in graph theory or in probability, stochastic processes, dynamical systems, and those things are very important aspects of developing these of the models. What do we do as a modelers? I mean, we talk about something we call it as tipping point. And it's a beautiful book by Malcolm Gladwell in 2002 that came out, and the title was Tipping Point. Tipping point means how things tips to the drastic things. For example, coronavirus was a tipping point and it brought the life to stand still. It was a tipping point. If you are seeing in the general in a big ways, but same way, if you study a smaller problems, let's say, how is the pathogen spreading, coronavirus spreading in normal, for example, in the normal city. It's a smaller problem than looking at a worldwide. And in that case, that also can involve tipping point aspects. In mathematics, in infectious disease modeling, we use a word called as R0 or reproduction number, which is similar as a tipping point. Equations and dynamical system, it's called bifurcation analysis. You talk about when the system turns, tips off, and that's so in all our fields we do these things, but we see it in a different glasses. We see it in different glasses. So I think this is very, very important. And this tipping point, Malcolm Gladwell, is a beautiful book which talks about real life examples. It is not a mathematics book, by the way. It's a general book which talks about how the system tip off, why certain places the riots, I mean, few fights, it starts into a riots, whereas the same thing in the different place, it may not become as a riots, for example, few fights between people. So it talks about from a social science angle, and it's a beautiful angle to understand the mathematics. To the students, I want to ask, who's the students in the Zoom today, what is the common things about these pictures? What can you see which is common in these pictures? Can you guys see anything common in this picture or in these set of pictures? Well, so I will take, so I think the pause I am giving just to you to realize some of the aspects here that, well, the thing that I see common is a word model. The word model. How is it common, word model? Well, in mouse is a model for a biologist. They do experiments inside the mouse. So that's the model for them. In engineering, as a small cartoon or as small building blocks of the big things like this toy train is a model for in engineering. In social science, it's a flow chart. For a mathematician, it's equations. So these are big issues. The choice of the word or the terminology that we use in the field decides on what many times when we talk to the interdisciplinary fields, people use the common word, but they have a different interpretation of the word that they use in it. So the model word for us is equations, but not necessarily is the same meaning for other people in the other fields. Models of infectious disease primarily has evolved in the last 2-3 centuries, actually. The first model was actually done by John Grant. He took the mortality from the municipal corporation, the different types of mortality, and he made the table, simple table, in which he stratified mortality due to what causes. He stratified the collection of all mortality into a tabular form where it was saying mortality due to starvation is this much, mortality due to smallpox is this much. And that tabulation was a model at that time. So very simple. So the point is, when we talk about model, it's not necessarily the complex equations that we write is always a model. Model could be how you better understand the real life aspects in a better way. So, and through that period of time, there has been Daniel Bernoulli's that has built a models for smallpox, but then also William Farr, he talked about contact processes in the diseases. But recently, or in the last century, basically, Ross and McDonald, Ronald Ross and Cormac McHenry's were the pioneer in developing these foundations of modeling infectious diseases. In fact, Ronald Ross, he was a Nobel Prize winning person, but also he was a medical doctor, by the way. So there are lots of theory of modeling that has been discovered in some sense by non-mathematicians, medical doctors, for example. So thinking about that, a mathematics is my field only. It's a very difficult aspect. It's actually people in other areas are also trying to understand some of the complex issues of mathematical modeling. Okay. So what do we do as a mathematical modelers? I mean, what is our task? I mean, we know these things, but I think the important things here is to, we do our task. If you see these red, these things, box, red text, these are the aspects of the mathematical modelers. It's quantitative modeling, basically understanding the biology or real life, writing down the equations. That's the lot of stuff, a lot of time we spend in that. And then doing mathematical and statistical analysis that links the models to the data, and then evaluating. It is very simple diagram to understand that. I think these are the tasks. But do we know how much time we spend in these models, in these aspects, in these components of it? Well, the first two aspects, 1 and 2 here, 1 and 2 is these two, we spend the most amount of time, 1 and 2 aspect. This takes a huge amount. That has nothing to do with the equations. That has nothing to do with the equation. That has nothing to do with the mathematics. That takes a huge amount of efforts to build those things. And then we have a significant amount, 25%, about doing a mathematical modeling task. And then there is also an important task is a presentation of results. How do we tell about storytelling from our results? And that becomes a very critical aspect of it. So I think this is very, very important for a person to think who is new to the area of mathematical modeling, especially students, to focus on how these things kind of help us to structure our learning process in the time. So let's talk about quickly on current COVID COVID-19 pandemic, you see this thing. What you see is on the x-axis, on the horizontal axis, it's a timeline, and in the y-axis is number of deaths, average deaths, and it has changed over time. If you see the US is this gray region here. US is this gray region. It is contributing now less death as compared to Brazil, for example, or total Latin America, or even India. But initially, they had a large amount of death rate in that. So, so these graphs shows that, yeah, it is under control, but still we are the best in the world in terms of public health care. And so we have to be more advanced in terms of preparedness and we are actually very good. US is very good in modeling, mathematical modeling. And so we can use many of these tools to address some of these, why these things are happening. So I'll come back to what is going on right now. So first of all, why did world shut down for the COVID? Why did this happen? Well, but it didn't happen in case of Ebola, SARS, and swine flu, for example. Well, one reason why it didn't, because SARS and MERS were deadly, but not was spreading easily. It was not spreading easily, but it was causing a lot of mortality. Swine flu, on the other hand, was spreading quickly, but not was deadly. Ebola was very severe, but was very difficult to contract. It was very, very difficult to contract. In fact, we have flu that causes a huge burden every year. We don't care too much about flu, but it causes 60,000 deaths every year, almost, roughly speaking. And we don't, and many 810,000 of cases that are hospitalized. And in fact, in coming December and January, our healthcare system is overcrowded of the flu cases, overcrowded. Well, there's a reason why don't we worry about. And I already explained 1, 2, 3, 4 points differing the other diseases. But flu, let's take the flu. Flu is less infectious. That means spreading less. So 1.3 versus 2.5. That means R naught means the number of people that one person is infecting. 1.3 person infecting versus 2.5 people infect. So these are spreading a lot. COVID-19 is spreading a lot. Also, one of the major reasons in why the shutdown happened is because asymptomatic cases were causing a lot of infection, not symptomatic cases, but asymptomatic. And asymptomatic period is larger for the COVID-19. Hospitalization rate is much higher for COVID. And of course, fertility rate is also very high. So these all reasons are making us more prepared in it, even though we are not yet there. I mean, now actually we have crossed much more than what annual flu is. But we are now worrying about flu and COVID coming together. Think about coming December. It's a huge problem for our healthcare system. So what do we mean by healthcare system a huge problem? So let's understand that point. In fact, the best way to understand is from our past mistakes and past experiences, basically, I would say. So one thing is 1918 Spanish flu is we can learn many things from influenza, Spanish flu. What can we learn? For example, there were two cities, Philadelphia and St. Louis. Philadelphia, if you see on the top right graph, Philadelphia waited for 2 weeks to start implementing policies. After the first case got detected, Philadelphia waited for 2 weeks. Whereas St. Louis, on the other hand, quickly implemented the policies in social distancing policies in just 2 days. And so look at the size of an epidemic here. Philadelphia had a peak early on, very high number of cases, whereas St. Louis has very low, but shifted to the right. And why is this was helpful? Of course, there's many ways it helped St. Louis. One thing was flattening the curve. The flattening the curve is the term that we start understanding it during 9/11 times. Remember 9/11 times that happens, the terrorist attack? after that, there was many problems, economic problems, and then there was a SARS outbreak in 2002, 2003. The US government in that started to build a preparedness task force at that time. In 2004, it has built. And that is the time it was decided that that task force was very critically designed in terms of they have anthropologists in that, they have epidemiologists, they have mathematicians also on that task force. And they actually started to build models for understanding any type of attack. It could be infectious disease attacks, like people were thinking about a smallpox attack. Smallpox is the only human disease that has been wiped out, but it is very deadly disease. So they were trying to model smallpox. They were trying to understand past epidemics, but the preparedness task force collected all the skill set at one place. Today, we don't know where to go because preparedness task force is kind of dismantled over a period of time because of funding sources and political narrative. But that task force was truly a first task force to define, to make understanding of these outbreaks. So what they did, they termed the coin, they started talking about something called as flattening the curve at that point. And that's how the term, the flattening the curve starts to pick up. So in 2005 onwards, they were talking about. So when they started, and then that is the time actually this figure was created, by the way. These pictures of the Philadelphia and St. Louis, that preparedness task force actually did those things. And they realized a couple of things. If you intervene on interventions early on, there are many benefits. First of all, the peak is reduced, and this dotted line is a capacity of a healthcare system. So you bring down the peak, but not only that, the area under the curve is reduced. Area under the curve. Not only every person who is infected get a healthcare facilities, but also the number of cases, area under the curve is reduced, means the number of cases are reduced. So that was an amazing discovery at that time of understanding what happens early on. I mean, logically it makes sense, but one needs to prove it through mathematical analysis that that is the case. And that was proven by that task force. So this is very important and how it evolved. Well, when COVID started to come, there were many models that come into picture. And the first one was University of Washington Institute Health Metrics and Evaluation. Now, when we say mathematical models, there are subfield in mathematical models. There is a statistic field, there is a mathematics field, and mathematical models are very different than statistical models, by the way. So the first model that came into picture and the US government started to use were a Health Institute for Health Metrics and Evaluation model. And that was a statistical model. This was just fitting a linear data to linear curves or statistical regression lines to their data, basically, and predicting it in the future. Okay, so this was the first model, but there were lots of issues with these models. It was unable to capture the true dynamics, true interaction of peoples and how policies are getting implemented. It was unable to capture it properly. And it was a huge confidence interval in the prediction they were giving. So they were way off. They were unable to predict what will happen in the US early on. Second one comes, the most important model was Imperial College models. And it was more dynamics models. It was a mathematical model, not a statistical models. It was a mathematical models because it was taking a mechanisms into pictures, mechanism of how people interact with each other, what do they, how much is the incubation period, different type of non-linearity that they were building. Mechanisms is the non-linearity, by the way. That they were building in the models, but they were also off. They were also off. They could not predict the true outbreak in the UK, for example. They were doing it for the UK. And the reason was this model was huge, complex model, multi-agent, but the data was not even available at the period of that time. If data is not there, you cannot if you have a complex model, you have many parameters, you need much more data to estimate each one of them. So there's lots of error you are making in that while estimating the data, and therefore you are unable to predict it. So these was good mechanistic wise, but the data limitation made it quite limitation. So the decisions was not good. So there were many things that we learned, but even if not learned in many ways, one was basically we cannot, first of all, we cannot put too much emphasis on prediction. When we talk about mathematical models, we want to understand how the disease spread, not how many cases will be there, not necessarily how many cases will be there a month from now, for example. That's not the reason why we build. We want to build what is the tipping point of the system, what is the, what drives the disease, what do not drive the disease, for example. So, for example, demographic factors could drive the disease. For example, environmental conditions. For example, a climatic condition can drive it. So what is driving the system more is what the understanding that you want to know from a mathematical models rather than prediction. Whereas most of these, couple of these models were focusing on prediction purpose. That's where they were kind of, especially early on when you don't have too much information about the disease. You can also study, instead of prediction, you can also study comparison of evaluation of strategies. If I give this strategy versus A strategy versus B strategy, which one is good? Now, absolute numbers may not be correct, but it can tell you it is 4 times better or 3 times better. One policy is better than the other one. So that's the rule. So anyway, so this was the things that came into picture. I hope it is not too boring for everyone. Okay, so coming to very pieces of it, and some of you might find it very simple, but I have to give it just for the completeness further, nuts and bolts of mathematical models. What goes, how do we prepare the models? The models, if we want to talk about, it's a bookkeeping exercise, first of all. It's a bookkeeping exercise. It's saying at time t plus 1, if I want to know how many people are there in time t plus 1, then we are talking how many people were there in the previous time, plus how much birth happens, how much deaths happen, how much immigrations happen, how much emigration happen. And that's, some terms are positive and some terms are negative. It's a bookkeeping exercise, just like this bucket of water where 2 taps are filling in and 2 taps are leaking out. Birth and immigrations are the ones which are filling up, and we are interested in knowing the levels of the water in the bucket. That's it. This is all the modeling is. This is exactly all the model is. Now you have to know what is birth, what is death means, what is immigration means in terms of the application that you are talking about. So let's talk about it from an infectious disease process. So in this case, we have 3 buckets, S, I, and R. S stands for number of susceptibles, I stands for number of infected, and R stands for number of recovered. And there are 2 tabs here. The tabs is called transmission tab, and the other tab is called recovery tab. And these 2 tabs will either leak out or fill in these buckets of people. This is basically the way we model real life population where the infection is spreading. So we divide the population into 3 types of people: susceptible, who have not yet got infection; I, which have got the infected; and R, who have got the infection previously and now recovered from the disease. Now, how do you build the transmission and recovery tab is all the innovation that involves the role of a mathematical models and the learning of a biological and epidemiological information. So, for example, the population structure information can go, pathogen biology can go into it, host population size, contact rates, pathogen infectivity. These all things can go into the development of the non-linearity function of the transmission and recovery function. The simple way to do is to take just a linear function for transmission and recovery. That's a simple way. Now think about it. How will you go from S to I? Is by, first of all, there has to be people in the susceptible class. If there is no susceptible class, there was no, if there is no water in the S class, there is no movement through the water through the tap, transmission tap. So it has to be a function of S. By the way, these are the parameters of the model, basically. So Gail, how much time do I have, by the way? Just, I don't want to overburn.
Oh, you have 20 minutes. No
Okay,
problem.
20 minutes. So, okay. Quickly, so the question now comes, so this basically, this differential equation that you are saying is basically keeping track of bookkeeping exercise. ds by dt is rate of change from how much leave, how much things leave, minus means leaving, plus means coming in. Whatever leaves here comes in. So I has two terms. This is the lambda term and this is the gamma term here. Okay. So what there are two tabs in I, and there is a single tab which is leaking out in the S class. So there is just single tab which is having a minus term, basically. And this is one thing to note here is that this differential equation has S times I. I told you, if there is no water in it, you cannot have water moving to the I compartment, right? So that means S has to be there. S is the amount of water in the S. Okay. Now, infectious disease, it's called infectious disease, not the chronic disease. Chronic disease, you don't need to infect anyone. Infectious disease, you need someone to infect it. So, so it has to be multiplied by number of I also here. Okay. Anyway, so the point here is, if you see this curve and the COVID curve, this is until June 17, you see the two things. European Union curve has gone down dramatically, whereas US curve is still on the higher level. So the shape of the curve is very different. Shape of the curve is very, very different. So the question is, what type of models what type of boxes I should use so that I get a proper shape in it. So if you see on the top right, if I use these three bucket and this type of differential, I get this simple one peak like the European Union case. You can see that European Union is very good fit using this model, but not necessarily United States, right? US curve is not looking like this I compartment here, right? So there is something more you need to do in this model in order to capture what is happening in the US, for example. So data guides you building a models, for example. One thing to note here, there is a quantity that one could compute, which is called R0 or reproduction number, which tells you number of new cases one person is generating. Basically, it is taking how many people goes inside I and how many people goes out. Divide that ratio is what reproduce. If this number is greater than 1, then that means more people are coming in and less people are going out. Right? If it is less than 1, that means more is going out and less is coming in. Very simple idea. So if it is R0 is greater than 1, there will be a peak of an outbreak. And if R0 is less than 1, then there is no peak. No, it will decrease. If it is less than 1, more comes out of it. It will decrease. Okay. So that's the whole idea. How many coming in and how many going out? And that's called as tipping point or bifurcation or whatever. Reproduction number is what we call it in diseases, basically. Okay. Now, one beautiful thing about this number, which we are computed it using a mathematical models, is the higher the value of this R0, the early the peak is. You see these red curves, the larger value of R0, the higher the peak is, and more the cases. Remember the difference between Philadelphia and St. Louis? Exactly that is the difference that we observe the value of R0. Okay. Anyway. So anyway, we can make this model, as I said here in the previous graph, this model was not good for United States, but was very good for European Union. So how can I change this model to make it good for the United States, for example? So for example, there are different types of models that we use here, list of the models. You can add on it, for example, remember what was the main thing in the COVID? What was the main thing I talked about in the COVID? Why is the COVID start to become a big deal all of a sudden? whereas previous disease does not. One of the reason was asymptomatic cases. People who are not showing symptoms are causing many, many cases, right? So in the previous model, that was not there. So if I include E compartment here, that takes into account that part. You can see the E compartment here. That takes into account why the how to capture the US curve, for example. So the US curves can be captured by SEIR model rather than SIR model. And E here means people who are not showing symptoms, and I here means people who are showing symptoms. Two differences in that. Now you can make this modeling exercise very, very complicated, and it can go very detailed. For example, you can model environmental reservoirs such as cholera. Cholera is spread by water bodies. So you can incorporate water bodies here. You can incorporate like malaria or West Nile virus that is spread by mosquitoes. You can incorporate vectors here, vector population. So these models can become very, very complex. From a mathematical angles, I could simply tell you one simple idea. If you add this only S and I compartment, if two buckets are there, then the shape of this I compartment will be logistic shape. It is called as a S-shaped, logistic. Whereas if you add a recovered compartment, the shape will be a peak of the I compartment. And if you add birth and death, you will see the damping oscillations in the I compartment. Beautiful mathematical construct that explains how you add simple things in the model mathematical equation, and it gives you a shape, beautiful shapes that you are practically observing in the field, basically. Okay. So anyway, so let's go into COVID-19 research example. This is more interesting. One of the things we are talking about is the herd immunity in the population. Herd immunity, we are talking about Sweden versus rest of the countries. Sweden is saying, we will just don't do anything and let's have this COVID spread through our population and we will find a herd immunity. What is herd immunity? Herd immunity is very simple idea. It is saying how many people are immune to the disease. Basically, the assumption in the Sweden is once you get the disease and recover, you are not prone to reinfection. You cannot get infection again. And so you are immune to the disease. And if more and more people are immune, the one infected person will not be able to get in contact with more susceptible person. There will be lots of immune people around the person, and therefore the disease will not spread. Okay, so the question is, how many people you need to be immune in the population before the epidemic can be controlled? Typically, what we do is through the vaccine. For example, on the top left graph, if you see measles vaccines was introduced in 1968, around 1968. And measles incidence starts to come down drastically with the rise in number of people who are vaccinated. What is vaccine doing? It is making people immune. There's two ways you can get this immune, by vaccination or through getting an infection also, naturally by your antibodies. So in this case, it was vaccine that was making the population to be immune or herd immunity to gain. Whereas in COVID, there's no vaccine. And so we are looking at natural way to get immunity, and that is through getting infection in some people. But one thing we forget, some people will die from it also. And that is not what we are understanding. And that's what people are debating, that Sweden policy may not be the perfect one. Okay. So the question is, how do we come out with this number? And mathematical models play a very important role. So again, R0 is how much is coming in and how much is going out, ratio of that, right? In the I compartment, what size of the population? If it is greater than 1, then there will be a peak. If it is less than 1, it will course down, right? Okay. So suppose there are, now if I reduce the number of susceptible to a smaller amount, we say the few of them are immune to the disease. Let's say not all susceptibles are able to get infected, only some of them, because some are immune to the disease. And so if I reduce now my B, which was initial coming in the rate, B was the coming in rate. If I reduce now B by 1 minus P, that means less people are now getting, P people are P people are immune to the disease or vaccinated, let's say, then we need to bring this number less than 1 in order to control the disease, right? So very good idea. If you use this formula, I can find what is the value of the P. So R naught, reproduction number for COVID, is 2.5. So if I substitute 2.5 in this formula, I get P, it has to be greater than 0.6, which says 60% of the people need to be immune in order for to control the COVID outbreak. Beautiful idea from mathematics that is coming in here. So a simple idea that we are using in mathematics. In fact, we can compute same way. People need to be vaccinated for measles. 95% needs to be vaccinated in order to control the disease. Polio, 85%. Their reproduction numbers are given in the first column, by the way. For example, measles is the most infectious disease. What that means is one person is infecting 18 other on an average. So it's the most infectious disease, whereas COVID is only infecting 2.5 other people on an average. Well, I have worked on Latin America a lot. I'm working on Ecuador, for example, in COVID, and we are working on how do we control the disease. Gail, I have like 10 minutes or 5 minutes or 2 minutes.
Well, about like 5-6 minutes.
Okay, awesome. So these are my students at Arizona State University that Caesar has graduated with PhD, and he's now in University of Virginia postdoc, whereas Carlos and Jordi are my graduate student. They are still working on their PhD work and on the projects. Also my colleague at Precision Hair and a parasitologist at University of Notre Dame, Edwin Michael, that I'm working with on this study. And the idea was, how do we understand this growing outbreak in the different provinces of Ecuador? Provinces are like a state in Ecuador, by the way. So that was the whole idea. And we used a simple, it was very starting early on this study, because now it might not be. So early on, we used a simple ideas, dx by dt is equal to lambda x. And if you solve it, it's an exponential function, right? And if you take a log on both sides, it's a line, a straight line in the log, right? In the time and the log of x, basically. Okay. So this is the model I used whereas, well, some outbreak are going exponentially, whereas some other outbreaks are not. In different provinces, it are behaving in a different way. So how do you assume that it is going exponentially, growing exponentially? Well, then we put this parameter P here. If you put the parameter P and find out the solution, basically what it gives you a polynomial solution. It is now a polynomial. So what it tells you, what is the order of the polynomial? So P is equal to 0 will give you a line equation of a line by this differential equations. And P is equal to 1 means exponential model. And any value between 0 and 1 gives you polynomial, different order of polynomial. Okay. So this is the model we used in a different data sets from different provinces and try to find out what is the rate at which it is growing. Is it exponential or less than an exponential? It helps in preparedness. How much effort I need. If I have $100, where should I put my effort? So these are some of the curves from two different processes. I mean, the process is simple, but I think the idea is what. In fact, we build a more complex model, the same idea, SEIR model. If you see here, SEAIR has a different, E means latent, but not infectious. A means latent, but infectious. Latent means asymptomatic. I means infectious. Q1, Q2, Q3 are quarantine. And Q4 is isolation. H is a hospitalization. C is critical care. So we have very complex ideas in this thing, and we were talking about preparedness in each of the provinces. I just wanted to show you how quickly it can become very complex. In fact, I talked about flattening of the curve epidemic. Typically, if you don't do anything to the infection rises exponentially. But then there is a time comes when we start to do social distancing policy, then it kinds of flatten up. So this is a beautiful graph that you are seeing, and it rises exponential in S1 region, and then a polynomial in S2 region, and then a linear in S3 region, and then becomes a constant function flat. This is the trend of a typical epidemic. How do you capture it? And when is this S1? When is this S2? When is the S3 is what the main idea is. The flattening curve is called as here. When you are in the polynomial phase, then it is called as a flattening curve, basically. Okay. I also worked with the social, airplane model, as I was mentioning. And here the delta on April, I think it's April 13, comes out to be a new policy. All of a sudden they decided on a policy that, remember, all the airlines have their policy of boarding. Some have 3 boarding. For example, American Airlines versus Southwest Airlines. Southwest is random. Whoever comes first boards it. So which is the good boarding policy that will generate less number of cases? Delta Airlines was not modeling. They were not thinking from the infection perspective. They were thinking from the bucks, from the money perspective. So we studied these things, and their policy they came out, which was, we showed it was not correct policy from an infection control policy. But anyway, so I will not go into the detail of this thing. I will skip this part, and I will talk about, so just to give you a final result, that we took into account 1 zone boarding, 6 zone boarding, back to front boarding, back to front business first boarding, different types of boarding. And we used a model, mathematical models, to understand how many cases will be generated in the movement of the people, basically inside in a different boarding. Okay. We are also studying now the use of mask in that. We are using complications, so drop size, particle size are very important. The wind speed are important. The contact distance is important. And there is a Hill function, which you use in the mathematical models quite a lot. And the complications in these models are quickly growing to precisely what we can say this will be the trend of infection in the flight. If it is 2 hours flight versus 1 hour flight, if it is smaller plane or big plane, and so on and so forth. Well, I will end here, but I want to give a piece of advice on these things, is that what I wanted to give a big picture for a modeling world, what we do as an infectious disease. Not only we are only focusing on equations, but we are focusing on other aspects that also go in. As advice to people in the undergrad, this Forbes magazine articles list 4 things, which 5 things actually, these numberings are incorrect, which are very, very, very critical for us to do algebra. You have to have a patience for doing algebra. Lots of calculation. You should, because many of us can do it, but sometimes we don't have a patience to do a lot of algebra. It is very important in the modeling world to do that. Learning a little bit of statistics. If you are in a mathematics degree program, you have to learn some statistics. Programming is very important. You should be knowing a programming, and the best way to know free softwares like R, Python. These are so popular in anywhere. And today we are considered illiterate if we are not knowing a programming in some sense in a job market today. So these things are, and communication is one of the very important things. Getting involved in the research helps you learn all these things, the top 4 things, if you get involved in the research very early on. Why do we stress? We as a faculty stressed on doing the research early on. This is all things we are teaching indirectly, by the way. So I will be teaching a course next semester. Basically, it will be a modeling and simulations in the department. And it is very different flavor. I actually make, it gives you how to find a jobs, to how to write a research papers. And I will be having instructors from other disciplines that will be joining us from time to time like from economics field, from tropical health to public health to CDCs, and many different countries. So the perspective, when we hear the perspective of other people, we get to know what exactly we are discussing. Otherwise, we are in a confined space of our own understanding. Very quickly, I have written some work in the Siam News, for example. He was my graduate student, Bashir. Here we actually collected the data. We did a social surveys and collected the data ourselves. Not only the modeling, mathematical equations and analysis of this and simulations, but also collection of data that we did. And that's why I wanted to show you. And Siam had a big piece on this thing in 2017, for example. I was through the wormhole with Morgan Freeman. We had a paper on a mass killings on mathematical modeling in PLOS One, and they interviewed us on how the mechanism that are driving the mass killing, what is the contagion effect. We were using the same idea because we all hear from same idea from infectious disease, that it is a contagion process, infectious process in mass killing, because we all see the media, and some people who are very prone to it would have a negative impact on us. And so we were quantifying that contagion process in that, and that's what the interview was about. Finally, this is final slide. I will not take much of your time. And this is the upcoming webinar series that is on education and pedagogical practices, practical problems. These are pioneer distinguished speakers for it. And it's actually part of the department because we are all at Illinois and we are organizing it. Professor Rakman and me and Sarah also is a part of it, and others, Dr. Aditi Ghosh from University of Wisconsin Whitewater, Dr. Padmanabh Shishir and from George Mason, and Rebecca Pearl in Arizona State. So with that, thank you very much for having me. I hope it was interesting to some of you, if not all.
Thank you very much. That was very interesting. Yeah. Do you guys have questions, especially undergrad students?
Yeah, I know it is quick. It's a lot of things in the short span of time, but again, I'm part of the department, so you can approach me anytime. It not have to be right away. And of course, it is recorded, right, Gail? It is recorded?
Yes.
Yeah. So.
I guess I have a quick question. In your average model, how many different of these buckets or nodes do you have? I noticed in your picture, it looked like maybe you had something like 10 or 11, but is that standard for the papers that you write, or?
No. It is, see, there's no one size fit all. Okay. It depends on your research question.
Right.
Okay. If your research question is about, see, that's what I was trying to show here. That's actually a very good question you are asking. Yeah, this one. So you see the US curve is not like the red curve in the top, right? Whereas European Union curve is very similar. So this model is fine for European Union.
Right.
It may not be good for United States. So you have to understand what is the features that makes it distinct in the United States and then in European Union. And you have to do some kind of, you have to try various demographic and epidemiologic characteristics to understand. For example, built-in incubation period or asymptomatic time, right? That is what I was showing in the box.
Right. Okay, perfect. Thank you.
Other questions?
Yes, I think I have one question. So, Dr. Mubai, when you were discussing the Sweden approach to solve the COVID infection problem, right? So like their approach was to just let the people get the virus and try to get this natural immunity to it. But what about those people who are able to get COVID again? Because I heard that, like in case of the US, there are people that can get reinfected with this virus, and how would this affect the flattening the curve and all that other stuff?
That's a fantastic question. And I think this is, you know, as we go in the outbreak, sometimes we don't know things about, and we are learning because this is a new outbreak, new pathogen. And so if you don't know, then you cannot build it in the model, right? But as far as if we get to know, for example, in COVID, the reinfection is possible, let's say, then, for example, this model would be better. SIRS model will be better, right? This is one thing. Second thing is we don't know at this point. We are unsure of whether reinfection is possibility or not. What is happening is the test for the COVID was not perfect. The test was a problem. And so they were identifying some cases as a case because what happens is there is called as antigen-based test. Antigen is the body parts of the virus. Think about after the virus is gone, the body parts in the body remains. Some of those for some period of time. And if you go to the test, antigen test at that point, the test will say you have the disease, whereas you are not showing any symptoms. Okay. So the question now becomes is there are many flaws in that, and we don't know at this point whether reinfection would be a possibility or not. So this is still a debatable issues, and until we get the fact, I mean, we have to we cannot build hypothetically anything. Whatever the information, biological information is, that's why it is very important to be up to date on epidemiological aspects. What is exactly happening? And so based on biological aspects that are known up till that day and the research question in hand, you decide on a mathematical model to use.
All right, thank you so much.
All right, other questions? All right, so in that case, let's thank our speaker. That was very, very educational talks and very great talk. Thank you so much.
Thank you.
It's my honor to be, I mean, thank you for inviting me to give. I mean, that's why I introduced myself to everyone also. It's a good opportunity for me. Thank you.
Perfect, thank you.
Thank you.
I have to thank Anush personally for teaching 442 next semester. I was studying for several years. That's why I'm going on sabbatical next semester, actually. It will be such a nice new, blood into this course. And I'm looking forward to actually, sneaking into your Zoom sessions.
Well, it's very kind of you. It's as I said, I mean, it's you all have given me such a wonderful opportunity, and especially the courses that I like, and I'm fortunate to have those ones. So, and thank you. And I would be actually needing your help also more on this. So I'll be communicating more later on.
Excellent. I'm looking forward to it.
All right, and so thank you very much. And so hopefully we're going to have another colloquium very soon. We'll be in touch. So thank you and have a great day.
Thank you. Thank you.
Bye, guys.